In this activity, we'll show you one way of measuring the conduction velocity of reflex pathways, and the reflex pathway that we'll use is that of the Achilles reflex. The equipment that we'll need is some abrasive gel, some tissues, some ECG electrodes, and some alcohol swabs. We'll also need an electronic tendon hammer plugged into a power lab, to which is also connected some ECG leads. Now we're going to be using these ECG leads to measure a myograph, in other words the contraction of a muscle, and the particular muscle we're going to measure is the gastrocnemius muscle. There are some written instructions for how to carry out this activity over in your CuraCloud notes, but briefly we'll show you how to go about that here. So let's have a look at how to hook up these electrodes. First of all, we'll remove oils from the skin using the alcohol swabs. And then we'll lightly abrade the area that we're going to apply the electrodes to by using this abrasive gel, and that just removes dead skin cells, which makes for better electrical conduction. We'll then wipe off the excess with some tissue, and now we can stick on the electrodes. What we'll need is one laterally, shown here, one on the belly of the muscle, and one medially. We're using these 3 electrical leads for this particular measurement. We'll put the white negative lead laterally. The black positive electrode we'll put over the belly of the muscle, then the green earth electrode we'll put medially. Now eliciting this reflex works well if you get your subject to put one knee on the chair and leave the foot dangling freely. So now if we go over to the next page of your CuraCloud notes, this is where we'll actually be carrying out the measurement. Now you should have made a prediction for what you think the conduction velocity will be after we carry this measurement out. Then you should see a written description of how to actually perform the measurement, and again we'll show you that here. And lastly, if you scroll down a little bit further, this is our lab chart window, and it is in here that we'll actually be performing our measurements. So to go through this step by step, let's click Start. And so now you can see data starting to come in. Now this response is fairly easy to elicit, but you will have to try to get your subject to relax, and that's what we're trying to do here. And then when you're ready, tap the back of the Achilles tendon quite firmly with the tendon hammer. As you do that, you'll see a deflection in the top channel showing when the hammer is striking the tendon. And then on the second channel, you should see a contraction of the calf muscle of the gastrocnemius. Alright, so now we're going to try to elicit the response, and you need to encourage your subject to just keep their ankle loose. And then what we'll do is we'll perform the maneuver several times just to make sure that we've captured a really nice clear response. You can see the foot of the subject plantar-flexing here, so that's looking pretty good. So let's have a look at the responses. You can see the hammer strike should be nice and clear, but sometimes the response from the muscle isn't particularly pronounced, so then just scroll backwards a little bit further and look for a better one. And here's a good response here, so the response of the muscle is clearly above the background. So now let's zoom in on the x-axis, and although you probably don't need to, I'm going to adjust the y-axis of this top channel. So now we can see that on the screen. Now we're trying to measure conduction velocity. The equation for velocity, of course, is distance over time. And so from this measurement here, we're trying to obtain the time. In the top channel we have the hammer strike, which is the exact moment when the muscle starts to be stretched, which is of course the stimulus which is being detected for this reflex arc. In the lower channel we see the contraction of the muscle. So in other words, the stimulus has elicited a nervous response from the stretch receptors in the muscle. That nervous response has travelled all the way up to the spinal cord, synapsed with the motor neurons, and then travelled all the way back down to the muscle, causing the muscular contraction. And so the time taken for that whole journey can therefore be measured on this trace here. To do that, take the marker and place it at the very start of the hammer strike, and then we're going to measure how long it took for the signal to get up to the spinal cord and back down again by clicking on this point select button and then moving the cursor to the start of the muscle contraction. And you can see down here that we get a time of 34 milliseconds. Now you can drag that value from the time box down into table 4 as done here. But just be aware the time that you're going to need for calculating conduction velocity is actually going to be in seconds. This data in table 4 is also in seconds. So rather than just drag the time down, which is in milliseconds, you're going to need to convert that into seconds. So let's type that in as 0.034 seconds. Now the text in this next part of the window shows you how to analyze the data, and there's an important point at step 7 which we'll come back to, but step 5 is telling us that the next step that we need to do is to measure the conduction path. So what is the distance over which these nervous signals had to travel? Now the spinal level, which mediates contraction of the gastrocnemius muscle, is at sacral level 1 or sacral level 2 or S1, S2, and so we have to somehow work out what distance that is from the gastrocnemius. So let's clear our electrodes off our subject and then take our tape measure. And what we need to do is work out on the surface of the body where is sacral level 1 and 2. Now hopefully from your studies in neurology you should recognize that the spinal cord isn't as long as the vertebral column. And so even though the sacral vertebra is down behind your pelvis, the actual part of the spinal cord that these nervous signals are traveling to is actually quite a bit further up the vertebral column. I actually find it quite hard to find a good chart that shows the difference between spinal and vertebral levels, but this is one here. Now what we want to do is to find some sort of surface landmark that might help us out to find where on the body S1, S2 is located at the spinal level. If you have a look on this chart here, you can see S1, S2 spinal level sits underneath the junction between T12 and L1 vertebral spinal processes. So we should be able to look up these spinous processes and in doing so find the spinal level that we're interested in. Now how do we do that? If you find the top of the alar processes and draw a line between them, as shown here on this skeleton, you can see the top of this alar process comes up to the bottom of the spinous process of L4. So if you draw an imaginary line across the alar processes of your subject, you should be able to find L4 spinous process somewhere in the middle there, and then count up the spinous processes until you get to the space between the spinous process of L1 and T12. On the skeleton here, you can see the rib attached to the 12th vertebra. Unfortunately, you can't see that in the living person, showing that we're in the right spot. And so this is where our S1, S2 spinal level is located. So going back to our subject, if you find the tops of their alar processes, draw an imaginary line between those two processes, find the center of that line and the spinous process you find there should be L4, and then count upwards to L1. Now, if you're having trouble palpating the spinous processes, you can get your subject to lean forward a little bit, and that makes them a little bit more prominent. Then, once you've found the point, which is between the spinous processes of L1, T12, use your tape measure to measure from that point down to the center of the belly of gastrocnemius. In our subject here, we got 77.4 centimeters. Now back at our Curate Cloud notes, we want to enter this into table 5 for conduction path. Now just be aware, we only measured the distance from S1, S2 spinal level down to gastrocnemius. Remember that the nervous signals, however, are traveling from gastrocnemius up to the spinal cord, then back down again. And so we actually need to multiply that distance by 2. And lastly, we'll convert that into meters. Now those are very simple calculations, so I'm actually going to leave that to you to calculate and to enter here in table 5. But now there's just one more thing that I need to remind you of, as noted here in point 7. The time that we calculated up in table 4 is actually the total time from when the stretch receptor generated the nervous signal to when the muscle actually contracted. But don't forget there's actually 2 points when the nervous signal isn't actually traveling along the nerve, so isn't actually contributing to the conduction velocity. And so we want to account for those 2 synaptic delays, and we'll do that by subtracting 2 milliseconds, so 1 millisecond each, from the time that we generated up above. If we subtract 2 milliseconds from that, that means that the actual conduction is occurring over 32 milliseconds. And so that's the time that we need to use in our calculation for conduction velocity. Again, I'm going to leave you to do that and pop your answer down in table 5. And lastly, on the next page, there's a handful of review questions which you should have a go at answering now.